Okay, PreCalc, for 9.3 day 2, we're working on sums of geometric series. And you're basically going to have two main formulas that motivate this whole thing. The first one is the formula for the partial sum of a geometric sequence. And you'll read about this in your notes, but I'm just going to write it up here so we have it for reference. It's a sub 1 times 1 minus r to the n all over 1 minus r. So with that formula in mind, let's work through exercise 71. So if you look at exercise 71 in your book, you will see it wants the sum from I equals 1 to 7 of 64 times negative 1/2 to the I minus 1 power. So this is a geometric sequence, and it's asking for the 7th partial sum. And if we use the formula above, we see that our a sub 1 term is 64. And then we do 1 minus r, and our r in this case, our common ratio is negative 1/2, to the 7 minus 1 power. Or in this case, I guess it's actually just the 7th power. So we're using this formula up here. So it's just to the 7th, all over 1 minus negative 1/2. So at this point, you can throw this into your calculator and compute it. I mean, like on a test, I'm looking for you to show me that you know what the formula is, you know how to plug things in. So if you plug this into your calculator, you will get 43. So this is just a partial sum of a geometric sequence, and we are using the partial sum formula. So you want to make sure you write this down, and I'm going to give you a sheet tomorrow in class where we'll have all the formulas on it. Okay, so that's partial sums. The second big thing in day 2 is infinite sums. So for this one, your formula is going to be just a sub 1 all over 1 minus r. So an important thing to note is that infinite sums of geometric sequences only converge if the absolute value of r is less than 1. Because if the absolute value of r is greater than 1, it's just going to diverge. It's going to go off to infinity. So with that in mind, let's do exercise 93. This is asking us for the sum from n equals 0 to infinity of, it looks like 1/2 to the n power. So this is just a pretty straightforward application of the formula. Our a sub 1, because there's nothing written out front, we can just assume it's a 1. So our a sub 1 is 1. 1 minus r, our common ratio, is 1/2. So this simplifies to 1 over 1/2, which is equal to 2. Which is kind of interesting when you think about it, because I mean, this infinite sum right here, what that basically is 1 plus 1/2 plus 1/4 plus 1/8, all the way through infinity. You add infinitely many terms. That is actually equal to 2. It never goes past 2. It just continues to approach 2 and becomes equal to 2. That's kind of an interesting fact about infinite sums. Okay, the last problem is an applied problem, and it's exercise 121. And it's kind of difficult, so I'm going to walk through it a little bit slowly. Let me scroll down. Okay. So exercise 121. This is it's a money problem. It's a compound interest problem, and it's kind of difficult because it's going to involve us coming up with a really, really huge sequence and finding the sum of that sequence. Sorry, I'm just pulling open my book right now. That's why I'm not writing it down. So problem 121, it says, consider making monthly deposits of $P in a savings account with an annual interest rate R. And it wants us to find the balance after T years if the interest is compounded monthly. So basically what we're doing is our P here, or the amount we're depositing every month, is $50. Our interest rate, R, is 5%, or 0.05. And the time that we're letting this money grow is 20 years. So if you read example 8 on page 666, you would know that the general formula for the amount is A sub n is equal to the principal amount, so 50, times 1 plus 0.05 divided by 12, and it's divided by 12, so our interest rate here is 0.05, and it's divided by 12 because we're compounding it monthly. So there are 12 months in a year, so it's divided by 12. And then up here, what we're going to have in the top is the amount of time, basically. So how many months is this compounding for? And what it wants us to find in problem 121 is if we deposit $50 every single month for 20 years, how much money are we going to have at the end? So the money that gets deposited in the first month is going to grow for 240 months. So for 20 years or 240 months, that money is going to grow. So the value of that initial $50 is going to be this number. And if you plug that into your calculator, I believe you get something like $135. The money that got deposited in the second month grew for 239 months. So if I deposited next month and I took it out still in 20 years, it would have only grown for 239 months. And that would have some value. And we're developing a sequence here. You can see. So like this is the money we deposited in the first month. This is the money we deposited in the second month. What this problem is asking us to find is how much money total do we have after 20 years. And so to do that, you're actually going to come up with a geometric sequence. So I'm going to see if I can scroll down a little bit. I'm going to have to erase a little bit of this. So I'm going to erase some of this stuff up here. So what we're going to get for our geometric sequence is the sum of 50 times 1 plus 0.05 divided by 12 to the n. And n is running from month 1 to month 240. So this is a partial sum problem. Our common ratio is this 1 plus 0.05 over 12. Our first term is 50, and we're doing the 240th partial sum. So in order to evaluate this, you're just going to use the partial sum formula. 50 times 1 minus whatever this number right here is. So you'd want to plug that into your calculator and figure out what that number is. Divided by 1 minus, I'm just going to call it r, and you can plug that into your calculator. Divided by 1 minus r. So again, I guess the crucial step here is to see that this really behaves like a geometric sequence, and we can use the partial sum formula to evaluate it. If you plug this into your calculator, you will end up getting something like $20,551.68, or something close to that. So yeah, that's how we bring geometric sequences to bear on problems of money. Is we try and look at the pattern, which is that we're adding $50 to the bank every month. and then turn that into some kind of geometric sequence that we can then use our formulas to solve. So those are all the exercises for day 2. We will see you in class.